Whenever you click a button or type something, it feels, well, instant, right? But what's really going on under the hood? It's this incredible, super fast journey from your thought to an actual action inside the computer. And today, we're going to pull back that curtain and see exactly how it works. So let's get into it. Right, so this is the central question, isn't it? How does an abstract idea, something you type like play this song, turn into, well, anything? How does it become a real action inside the circuits of a processor? That's the journey we're taking today, step by step. And this really just lays it all out, doesn't it? On the left, you've got our language. Print hello world makes total sense to a human. But on the right, that's the computer's reality. A whole bunch of zeros and ones. It's like they're speaking two completely different languages. So the first problem to solve is, how do we translate? Well, we bridge that gap with a really important translation process. And that's our first stop. Before the computer can do anything at all, our commands have to be translated into its native tongue. And you can kind of think of it like translating a book through a couple of languages. We start way up here at a high level with languages like Python or Java that are built for us, for humans. From there, it gets translated down into something called assembly language, a bit more cryptic. But the final, most crucial step is getting it all the way down to pure binary code, zeros and ones, because that's the only thing the hardware actually gets. So what is that binary code? Well, each little chunk of it is called a machine instruction, and you can basically think of it as a tiny, super simple sentence. And just like our sentences, it has two key parts. You've got the opcode, which is the verb. It tells the computer what to do, like add or move this here. And then you have the operands, which are the nouns, the actual data or pieces of information it's supposed to work with. Okay, so now that we know the language, let's meet the thing that actually speaks it. We're talking about the machine's brain, the central processing unit, the CPU. I love this analogy. It's just perfect. Inside that incredibly complex CPU, there's one part that's running the whole show. It's the control unit. And just like a conductor, its job isn't to play an instrument itself, but to make sure every other part plays its role perfectly and at exactly the right time. So who are the key players in this little orchestra? Well, you've got the control unit, that's our conductor. Then there's the arithmetic logic unit, or ALU. Think of that as your maths whiz, the section that handles all the calculations. The registers? They're like the sheet music right on the stand, super fast memory that holds only what's needed for this exact moment. And finally, the main memory. That's the entire library, holding all the music, all the instructions for the whole performance. And the control unit is there, directing all of them. All right, so we've got the language and we've got the brain. Now let's see how they actually work together. We're going to look at the process that every, and I mean every, single instruction goes through. It's called the instruction cycle. Everything your computer does, from playing a movie to sending an email, is built on this one simple four-step dance. It's a cycle. First, the processor fetches an instruction from memory. It grabs the next task. Second, it decodes it. It looks at those zeros and ones and figures out, okay, what am I supposed to do? Third, it executes the command, sending that job off to the right part of the CPU. And finally, step 4, it stores the result. And then it starts the whole thing over again. Fetch, decode, execute, store. Over and over. And this is where the real magic comes in. It's not that these steps are super complicated. They're actually pretty straightforward. The mind-blowing part is the speed. This little 4-step cycle doesn't just happen quickly. It happens millions. No, literally billions of times, every single second. So that incredible speed makes you wonder, right? How on earth do modern processors get that fast? Turns out, it's not just about doing that 4-step cycle faster and faster. It's about doing it smarter. Let's dig into a couple of the secrets behind that modern speed. Okay, so imagine the old way of doing things. A processor would grab one instruction and it would do the whole dance: fetch, decode, execute, and store. Only when that one instruction was completely finished would it even think about starting the next one. I mean, it makes sense, but it's really not very efficient. You've got parts of the processor just sitting around, twiddling their thumbs, waiting for their turn. This is where things get really clever. Modern processors use a technique called pipelining, and the assembly line analogy is perfect. While one instruction is in the execute phase, the very next one is already being decoded, and the one after that is being fetched. All the different stages of the cycle are working at the same time, just on different instructions. It's a total game changer for throughput. But
With all this happening at once, how does anything stay in sync? How does that assembly line move in perfect rhythm? Well, that brings us to the second big secret, the system clock. And thinking of it as the processor's heartbeat is honestly the best way to imagine it.
Now, this clock isn't telling you if it's lunchtime. Instead, what it does is generate this incredibly steady stream of electrical pulses. And every single one of those pulses is like the tick of a metronome. It signals every part of the processor to move to its next tiny step. It's the thing that keeps the entire orchestra playing in perfect, synchronized time.
And the scale here, it is just wild. That heartbeat, that tick, it's happening billions of times a second. That's actually what gigahertz means. So when you see a processor is, say, 3 gigahertz, that means its internal clock is ticking 3 times billion times every single second. Just let that sink in for a moment. So when you put it all together, you see this absolutely incredible journey. We start with a human thought written in a language we can understand. That idea gets translated all the way down into simple binary instructions. Those instructions are then fetched, decoded, and executed in this perfectly synchronized dance, all of it driven by billions of tiny electrical pulses every second. Every single layer of this process is totally essential to creating the digital world we live in. And that really leaves us with one last big thought. This whole process, it's constantly getting faster, more efficient, more powerful. So as this fundamental cycle of turning our ideas into actions keeps accelerating, what are the things that seem totally impossible to us right now that are going to become our new everyday reality?